Okay, so this is the third video in basic passive elements where we will overview the inductor. So an inductor is an element that really just capitalizes on a behavior describing the relationship between electricity and magnetism. So this is Lenz's law and Faraday's laws that you should have gone over in physics classes. And it really just notes that any wire or something that has the ability to carry electric current that passes alternating electric current generates a magnetic field. And so what we're doing is amplifying this effect in a sense by creating a multi-turn coil such that the magnetic field that is created about this wire as current is going through it is kind of condensed into a physical space that is slightly smaller, such that the magnetic field increases to the point that we can utilize it to store energy. So an inductor fundamentally is a multi-turn coil such that when we pass an AC current IS through it, we find that the voltage across the coil is going to be proportional to not only the magnetic field that's generated, but the rate of change of I. Okay, so this is due to, again, the electromagnetic field generated by the alternating current through the wire. So Lenz's law states that the field generated is the negative of the delta in the change of I versus time times the constant of proportionality, L. And this is what we're going to call the inductance. So the voltage potential is the opposite of the electromagnetic field in terms of polarity. It counters that. It resists in an analogous way that capacitors resist instant changes in voltage. Inductors resist instant changes in current, as given by this derivative relationship of current with respect to time. So we can write the voltage current relationship of an inductor as V equals the first derivative of the current through the inductor with respect to time times the constant of proportionality L, where L in this case is the inductance of the wire, and that's going to be measured in the units of henries. So now ideal inductor with zero resistance in it is again a passive element where we have a current going through the element and a voltage across the element. So if we expand this equation a little bit, we can check the units again, voltage in units volts, di dt is in amps per second, and Henry is the inductance, so we see that 1 Henry is 1 volt second per amp. So let's look at that inductor in a little bit more detail. So here I've drawn this multi-turn coil going around this rod. And so the parameters that we're interested in are the number of turns, first of all, around this coil. So that would be N, capital N. The length of this rod, so S, we'll call that the axial length. This is a helix. The cross-sectional area of the rod, or the core of the inductor. This could be air, or it could be some other material that helps sustain the magnetic field, or allows for the magnetic field to permeate through the material, for example. And then, of course, we're going to have the voltage across that and the current through it. So when we create an inductor using this method, we see that the inductance is going to be proportional to the number of coils squared times the area. So the bigger the area, the more inductance we have, inversely proportional to the length of that. The longer it is, the more that magnetic field is spread out. Okay, so the less the inductance. And then this physical quantity then multiplied by constant proportionality, which is using the symbol mu, which is what we call the permeability. Permeability of the material that the rod or the core of the inductor is made out of, which really is a measure of the capacity of the material to allow for the magnetic field so to literally permeate through the material. And again, we reference permeabilities of materials with respect to that of in free space and vacuum, where mu sub 0 is 4 pi times, which is in units of nanohenries per centimeters. So in this case, inductance per unit length. So I mentioned that a change in current, an alternating current, is proportional to a voltage, or at least a rate of change here. So, or the voltage is proportional to the rate of change of the current, rather. So this stems from Lenz's laws and Faraday's law of induction. So we can start with by showing that the inductance is proportional to the magnetic flux, which is due to the current through the wire with respect to that current. We note that the voltage is going to be proportional to the rate of change of that magnetic flux, and that's what Faraday's law of induction states. Therefore, we can write the expression that V is the first time derivative of the inductance times the current by doing some substitutions of this equation into this equation, and that's where we get that voltage is proportional to the rate of change of current versus time times that constant of proportionality, which is measured as Henry's, or which is what we call the inductance of the element. So note the similarities of this and the capacitor equation. For the capacitors, we saw that I equals C times dV dt. So we really are kind of switching the V and the I terms, and then of course changing out that constant of proportionality. So because of those similarities, I'm going to move through this section a little quick. But we note that if I is constant in this case, the first derivative of I with respect to time will be 0, therefore the voltage across the inductor will be 0 volts. In other words, if we have a constant voltage across an inductor, we know that the current, a constant current through the inductor, we know that the voltage across the inductor will be measured as 0 volts, which looks like what we call a short circuit. So that's like connecting terminal A to terminal B via a perfect conductive wire. So we can say two things. Time-varying current produces a self-induced voltage across an inductor. Inductors act like short circuits to DC. And then, of course, analogous to what we saw in a capacitor, abrupt changes in I are impossible because it would require an infinite amount of energy, in this case an infinite amount of voltage. So inductors resist instant changes in the current. So then we can go on and find the power and the energy stored again. Again, this is a passive element, but instead of the energy being dissipated, it's being stored. And in this case, it's being stored in the magnetic field that is induced across the element. Again, capacitors, the energy is stored via the electric field. Resistors, energy is dissipated via thermal processes. So power, the equations again look very similar to capacitors. We're just really changing symbols. So the power of an inductor is L times I times di dt. And the energy, again derived as the change in the energy stored in the magnetic field, is going to be 1/2 times L times the difference between I squared minus the initial I squared. And if that initial current is 0, then that equation just resolves to the energy stored in the field is 1/2 Li squared. Okay, as a final slide, I just went ahead and put together a matrix of these passive elements with a few important parameters or variables that I like to consider. I'm not going to go over this entire table in detail. They will be in your notes, as well as there's a few examples in your notes as well that I did not put in the videos. So make sure you review the slides that I provided on Blackboard so that you get those examples. But to overview this table, I'm looking at the electric symbol with the annotation of the passive sign convention, the VI relationship. And in this case, I've only put the simplest version of that VI relationship. Resistors obviously are the simplest, where we just Ohm's law, but I can write this as in terms of V or I, right? For capacitor, I equals C dV dt, and of course if I want to solve it for voltage, I have to rearrange this. So I could see that voltage is equal to 1/C times the integral of I, plus an initial condition, which is important. Likewise for the inductor, I put the simplest version of that down. But note that you can rearrange this in order to quantify the other parameter as well. The power, energy, a couple of interesting things about the elements that are important, I think. For example, that an instantaneous change is not permitted in the element's voltage and a capacitor's voltage. You can't have a step voltage change for capacitor. Likewise, you can't have a step change in current for an inductor. It would require an infinite amount of energy. And to a DC, the element capacitors look like open circuits, constant voltage, and inductors look like short circuits, constant current. And resistors, just resistors. Okay, they can permit anything really. So make sure you review this table, just become familiar with it. Note that you don't have to memorize all of the equations necessarily. If you remember I equals C dV dt, which is probably the one that's easiest to remember, and for these capacitors and inductors, probably the most important one. Capacitors are generally used more often. But if you remember this one, you can get to all of the other ones. You always just remember that power is V times I, so you could figure out these specific expressions if you wanted to. And then you remember that energy is just the integration of power with respect to time. So you got a few kind of main ones that you should remember, and then besides that, you should be able to repopulate this table and then utilize the equations in the right way. So make sure again you refer to the examples where you do some of those problems.